Okay, so I will give you a new link, which I think will work, and then we'll put it back on this channel later.
Oh, rip it and okay.
Yeah. Okay. Live. Aha. Now, here we go. Coming in, I guess, Zulip. Great. Yeah. And Natalia, you can just, I think, oh yes, do we need any groupoids covered? We're probably missing a groupoid. We've got, so I think, so Maddie is there, but maybe not on.
Maybe P. I haven't seen Jack.
Okay.
Oh, I see. Jack's here. Jack's here.
Okay. Great. And is that working? You can click on in the Zulip, you'll see a link for YouTube.
Let me check.
Oh, is it not there yet? You don't see it on.
Oh, I see it there.
Let me put it in chat on Zoom as well then. You can click on
yeah, we're there. Now I need to mute myself.
Exactly.
Delay, I guess.
Yep, 20-second delay, which is going to make it even more. I mean, you can like ignore it. I just want to make sure it actually works. So, okay, great. I guess you can. Yeah, I guess you can tell everyone the. Okay, you might as well tell everyone that what that link is. And then they might as well turn off before we start.
I'll post it in Discord.
Great, thanks. And then we'll toss it in all the Zulip things. And I think. Okay, and I will no longer look at YouTube. Oh, I see Allison is there. Okay. And
hello,
Allison.
Hey.
Now we are. Okay, that's good. So that is working. Now let me share screen, and this is the imperfect thing. Great. So that part is good. I guess we can see that. And I guess, is that?
Probably too late to ask this, but do you want to go landscape orientation for people watching on computers?
Yes, I could. I would, but I couldn't figure out how to make landscape on Notability.
Okay, gotcha.
Do you know how later?
If you just rotate your iPad into the landscape orientation, the pages will keep the same orientation, but you can, I think probably it's better just to run this one with the portrait one.
Do you mean like this? You mean the pages, the new pages will be landscape then?
I use GoodNotes, and if you just rotate your iPad, and the pages will remain in portrait orientation if that's the template you're using, but you can you can screen share from.
Yeah, unfortunately,
yeah, I would just leave it. I would leave it for today probably, and then.
GoodNotes I know very well, and yet I know how to do that there, but so unfortunately, one thing I did forget, the Dropbox link. So here is going to be. Let's see. Dropbox, why won't you let me click on it? That's a calendar. Okay, so let's see. So we're probably getting, okay, so Dropbox, and then, I know what I can do. It's not syncing. That's not good. Okay, so I think, yeah, and this is the thing I also find annoying. I have to figure out how to get rid of that eventually. But you know what I'm going to do?
And you see that your tablet's only showing half, right?
Yes.
Okay.
Or I actually didn't even know it was showing that. Okay, so there's the, okay, so there is my practice lecture with my beautiful pictures. And that one I have a link for. So what I'm about to do is do something. I'm going to actually do all my slides on this because I have a working link and Dropbox is already. So let me give you a link to this for them, and I'll just erase everything and start from scratch.
All right.
So share. Settings. Anyone can view, copy link. And I will, should I just send it to you? I will send it to you on Zulip and you can let people know.
Sounds good.
Great. Next thing to do is clear everything.
Does it matter that it says practice lecture? It's the same, it's the right one, right?
It is, well, it's now the right one because I'm just deleting everything. And because that's one that there is a working link for. My great pictures are going to be revealed. That's not good.
I have so many screens open. Like I've got the YouTube, Zulip, and Zoom going here. And,
I think you can close YouTube. You could potentially close YouTube, I think, now that one person's on it.
Yeah.
Because just so that someone can know if it goes down. So. Okay.
All right.
And then let's see, paper. Let's make it all blank. Okay. So great.
Sorry, so did you want us on YouTube as well, or only
Nope.
our?
I think you need only be on Zulip and Zoom, except for one person ideally could be on YouTube in case something bad happens. But I guess they can let us know on Zulip anyway. And right now, if all goes well, people can already watch on, have access to the slides if you've posted it somewhere, and they can see what's on the screen. And let me just send an email to a couple of people so they know who are coming on Zoom. And is anyone having trouble getting on? I guess it's 8:02, but I just want to make sure, is anyone having trouble with getting on as far as you can tell? Okay, Long Fei Li, I'm going to send him that, and then there is one person on email, and then I think I'll be good to go. And for people watching, if you are emailing me, chatting, or anything like that, I have no idea what you're saying because I'm not paying any attention. And let's see, the last thing I want to do is let the person know who, oh, of course I don't know offhand where that went.
Sorry, we're talking on the chat right now. Is there a problem with the fact that we can only see half of your iPad? Is that?
Probably not better. Can you see that? Is that?
No, I can only see half as well.
Oh, that is good to know.
Yeah.
Better?
Nope.
Let me show you what I see. Do you see an entire rectangle or only half?
Half.
Good to know. Okay. Okay, so in that case, I will do the following thing. Okay, if you can see half, then then you can see this, right?
I can't see that.
You can't? Can you see this?
No, I only see the front page. I only see the front thing where it says, it looks like half of your title is there.
Oh, sorry. You are at, wait. Now I'm confused because my actual iPad, which is allegedly syncing. Now I'm mystified. Sorry, everyone who I can't hear. So Zoom, I see something on my iPad. My iPad is allegedly synced. And
Let me see. Oh.
New share. Okay. So you can. So it's interesting because I see on Zoom the screen I'm allegedly sharing, and you don't see any rectangle at all.
So Quinn is suggesting to restart the screen share.
Good.
Yeah, I still see half. Jack, are you?
Just half, yeah.
Yep.
Okay. So here we go. Share screen again. Cable. Share. You are screen sharing. And I don't see anything yet. Here it comes.
There we go. Perfect.
Full rectangle?
Yep.
Excellent. Okay.
Let me just check. Okay, yeah, we'll have to wait a little bit, but I think it'll work on YouTube too. Yeah. So.
Yeah, only 20 seconds later before it appears. I think whatever we see, they will see. Okay. So, okay, great. So in that case, let us. Great, that's all good. Okay. Let's just start and see what happens. Great. So if all goes well, everyone can actually so it can actually see on YouTube. There's one person I would like to let know, but I guess I'm not going to worry about it now, and I'll apologize to him later, who's not on Zoom. But let's just try this out. So here is the welcome everyone. I'm writing this all on a new screen rather than having things prepared because that just turns out to be what ends up working. So we'll just go with that. So welcome. So let's see. Right now, people can just again check with the shepherds. You can see me in the slides, right? Or at least the slides. Great. Okay, good. Shepherd, just interrupt if you have interesting questions to say. So today, here's my plan. I want to basically set the stage, which means that if I think about what I want to talk about, then I want to talk about the course, about the pseudo course, and I think that will take about an hour, but I realize I shouldn't do that. So I'll talk about it a bit, and also talk a bit of philosophy about mathematics to also set the stage. And then finally, I want to start moving toward algebraic geometry, although I won't actually get there because I think category theory or maybe sheaves is as far as we're going to go. Okay, so this is the first meeting of this experiment, and for many of you like me, the experiment's a few weeks old, and so this will be a little bit different than the ones later on because I want to describe what might happen and how we might get there and what might change. So to set the stage, the ongoing pandemic arrived relatively suddenly and kind of overturned and disrupted a great deal. So there's a terrible human cost, and I hope everyone you love is safe and well. But I also know that for some of you, people you know are not safe and well. And also, I should mention our struggles in this new situation have made ongoing injustices more obvious in the US at least. But there's also some renewed sense of solidarity and that we're all into this together. So I'm doing this because there's an opportunity right now when things are grim to do things that are hopeful and do things that are new and try out new structures and habits that might last beyond the current moment. So, and so I'm following the lead of many people like Daniel Litt or Jared Alper and Isabel Vogt who acted immediately and tried new things as soon as things were shutting down. Okay, so here's the plan. So really, I'm thinking more, here's the game we're playing with the constraints we have, and we'll see how to proceed as we go. So my initial intent was to have an open, free introduction to algebraic geometry. And because I'd thought about it at a certain level, roughly in the US, pre-research, but otherwise advanced graduate level. And I have notes on which to, and I have notes I can use as a skeleton to build on. That's what I'm doing, and I'm doing it at this level because that's basically what I have to offer. And let's see if I do this. Great. And when I do that, that should ideally update the notes in the Dropbox too. Okay. So what is this thing going to be? I don't know if you've seen Marguerite's picture, Ceci n'est pas une pipe, but I want to say that this is not a course. This is not a lecture. And so we could take the traditional model, which is an academic course, and fit it to the circumstances and let that guide what happens. But I think it's not the right way to go. And I think it's a standard human mistake with new technology to try to use it in the same way as the technology we're used to. And so only when people are born into the new technology do we finally see how it's best used. So it's true for smartphones. It was definitely true for schemes and stacks, but we can still free ourselves from old models and try to see what the new ones actually tell us to do. So here's some guiding principles that I can think of. Also, those of you teaching in universities know that the academy is going through, I think, literally a couple of decades of rapid evolution in technology use after a long period of stasis. And we're doing this over a few months. And those of you who are students are experiencing the brunt of it. And it's not a pleasant process, but such is life. So, okay, so here's some principles that I want to let guide what we want to do. So the goal should be that it should be as available as possible to people, which means people with sufficient background. But that means that ideally we want too few technological barriers. And that also means ideally it should be free for everyone. And this is now possible thanks very much to the generosity of people who make things free. And also, in order for it to work, it should be as little work as possible for me around what's really necessary, because if it's a lot of work for me, I'm not going to be able to do it. And it also should be as little work as possible for you outside of the intellectual work of learning. So, so I don't mean it should be easy, but it should be, but all useless work there should be as little useless work as possible. And so other goals will be to try to invent some structures and experiment with them that make it easy, that make it somehow easy to learn or natural to learn. And actually, I should say Gal Gross in her sign up form mentioned this notion I looked up that really is great. You should look this up. It's a notion of a Schelling point. I don't know whether I'm saying the name correctly, to try to set up structures that guide people to doing good things naturally. And so this takes advantage of the fact that you're human, or most of you are human. So in particular, community building in many different ways, and making use of, I guess, the phrase is pure accountability, but just the fact that it's way easier to do things in a group. I find it way easier as well. And so something I want to discuss maybe another day is that mathematics is one of the most social of the intellectual disciplines. And people have this idea that have the opposite idea, but they don't know they have no experience with it. So this is what will be necessary to make things work. And then finally, the challenge that I am not sure how to deal with is that there's a way broader group of backgrounds than I expected. And we could just say, well, it's only for some people, but I think it'd be great if we could try to keep as many people as possible by doing things at several levels at the same time. So we'll see what happens with that. Okay, so that kind of sets the rules of the game. Now here's the structure of what the pseudo course might look like. Which is, okay, so we'll have pseudo lectures every Saturday or most Saturdays, and let's say until roughly early to mid-September. And that's actually not so many, of course. The amount of time in our Stanford quarter would take us about a third of the way into one quarter. But the difference is here, these are, given the principles, only a small part, even if they're a key part of the course. So they kind of can only set the stage for most of what actually is going to happen. So most of after that should happen in the built structures, the stuff we built up. And then basically it has to happen by self-organization. Although we'll try to give prompts or suggest things to try. And so mathematically, how is it going to work if people are all these different levels? Well, if you're not comfortable with writing proofs and coming up with proofs, it's going to be really challenging because this is not well aimed at you, but hopefully you'll still get something out of it. But if you've seen proofs and have used them and don't know what a module is, then I think there's really an opportunity here to, although it might be challenging. And I think it's a paradox that the people who have the least mathematical maturity, which is, as any mathematician knows, is not an insult. It just means lack of practice and experience, are going to somehow need the most in order to understand what's going on. As you can ask the experienced mathematicians who are present too, that somehow the more you know, the more comfortable you are with attending talks and watching things where you understand less. And it doesn't mean you just fall asleep. It means you actually have trained your attention to try to grab at those bits of information that in this vast ocean of confusion. So you can actually have something to hold on to. So at worst, maybe you'll get a chance to practice that, and also when reading, to learn how to read mathematically. And then if you're at the level that the rising C notes were initially aimed for, say roughly graduate level, but not necessarily a future algebraic geometer, or maybe an expert in a different part of math, then I think we can talk about schemes and get someplace interesting. So my plan for the next 8 to 10 weeks, though, is not to cover everything, so the story for this episode until September is going to be basically about what's the notion of a geometric space. There are various things we think of intuitively as a geometric space, and this could be things like a variety or a manifold or even a topological space, or if you're very fancy, it can be an algebraic space. If you're super fancy, it can be a stack. And so that, and to understand, to try to figure out what is the common way we use to talk about such things, and it'll be as a ringed space and I'll say, well, I'm not going to reveal the end of the story, although you can of course flip to the last page. And so the prerequisites to follow along should ideally be, so here's the prerequisites, is that ideally it's comfort with coming up with proofs. Ideally, it should be some commutative algebra, not more than ideally, I think, but not necessarily a huge amount, but groups, fields, rings, ideals, and modules. And I feel like the borderline might be tensor products, things that's something you might not have seen but can learn. Some point set topology. And then I guess some intestinal fortitude to figure things out as they go and to sort of figure out things you have not actually seen. Okay, so now I'm getting closer to actually talking about mathematics. So let me first talk a little bit about maybe idiosyncratic point of view on learning mathematics. And this, I don't know if it's a majority point of view, it's probably a minority point of view, but I think it's the kind of point of view I know the Shepherds, for example, have, and many people I know have, but it's maybe not quite Bourbakiste. So in order to try to learn as much as possible, so I'm going to try to explain as much as we need. And I'm going to try to explain as little as possible. So maybe I realized again and again that this slogan may be rearranged in different ways. I'm going to try to say as little category theory as possible, but as much as we need. So another thing that's important that I think when you, even some graduate students don't fully get yet, is that it's important to know what you know, and also know what you don't know, by which I mean be very well aware of things you don't know. Don't wave your hands. And a very big warning for in any class is if someone doesn't know what they don't know. So try to be honest and scrupulous. Don't try to impress anyone. know when you're waving your hands and feel guilty when you're waving your hands, but sometimes you just have to feel guilty. Understand what you can prove, don't just nod your head. And then how do we actually learn mathematics? Well, I guess traditionally what you do is someone will write on the board an axioms and then theorem and then proof and then another theorem and then proof and maybe a corollary. And that's, I know, not how I really learn or how humans learn. So what do we actually do? Well, we start off with some idea, which is vague, an intuition we're trying to understand, and then we'll formalize what we're actually talking about, so we can make precise what we're talking about, and then we abstract it to realize we're talking about something more about what the structures we're talking about, and then we realize it applies to more general situations, which lets us get better intuition. We realize that suddenly what we're thinking about applies to these other circumstances, which lets us understand things more and more and more. So, in particular, pure mathematics is really an empirical science. So you don't just make stuff up for the sake of making stuff up.
We got a request that you update the slides in the Dropbox.
That is a good, yeah, that's something which I was warned by Yufei Zhao that I have to get used all the time to do that. Okay, thank you. Yep. Please do that again.
All right, let me know I will interrupt you. All done.
Thanks. And also let me know if I start to speed up in speaking when things get more exciting. Okay, so great. So there's in particular, I think, this is at a conference in Sweden, not that it matters, but Sergei Shadrin, who's a mathematician now in the Netherlands, early in his talk said this thing as a slogan. He was very vigorous and he basically shouted it out, and I wanted to stand up and cheer, which he said, we don't want definitions, we want properties. So what matters are not definitions, but properties, and that properties, then the properties are what should guide what the definitions are. And I guess ideally, this is a picture of him, I guess, jumping up and down to say this. I guess he's saying his own name, it appears. And so related to this is the importance of naming. And so some things deserve, when you're young, you're told things and you just are supposed to accept them. This is a group. This is the definition of a group. Here are the axioms to remember. But in fact, some things are important enough to deserve names. Some things have names and really shouldn't have them. Some of them have the wrong names. And there's nothing wrong with disagreeing with the conventional wisdom on these things, or demanding that someone explain why you should care. And so in particular, the question you should always ask is, why is a group, not what is a group? And then if you know why a group is and what it's trying to capture, then you get the definition. And the definition may not, then you don't have to remember it. You just know it, and you may not have memorized the perfect axioms, but you will know something equivalent to them. That's all that really matters. And okay, so next thing is the notion I'm going to use of easy and hard in a non-traditional sense, which is if you think about things in mathematics in terms of what you actually understand, there are things that are easy, which means that they're easy to remember. You know how to, that you know without thinking how it works. Maybe it's a proof where you just follow your nose and it proves itself. And hard is something which seems to come out of nowhere, which you've not dissolved in your head to make it something natural. So easy could be technically very difficult, and hard can be technically very easy but very clever. So, but I think that's the real notion which matters for us. Okay, so now I feel like we're not. I still feel very guilty that we're not getting to any math yet, but that's okay. The next thing is you have to do problems. And it's that you have to get your hands dirty, and mathematics is not a passive activity. Feynman had a quote, which were on my slides, which I'm not using now, which essentially is that if you can't calculate something, you don't understand it. So the goal is not to recite something. You have to actually understand it and be able to find your way around it in the dark just using your hands. And in particular, there's a question of when you do problems on a problem set, and the problem I'm hoping you'll try now is a standard question is, I'll get in all sorts of classes is, here's my solution, now what's the right way to do it? And then the solution in question is several pages long, and maybe there's a 4-liner, but any hard-fought solution, even an incomplete solution, is actually better than a read solution, than it's something that's the right solution that you just read. You can always read the right solution after, but your understanding only comes with that after trying, and even failing is fine, but you have to fail before you look at the right solution. And so in particular, if there's a problem that you're discussing with other people and you don't know the answer, don't look up the answer. Just be satisfied with the fact that you don't know what the answer is and be bothered by that and worry about it later. Don't just look up the answer and take a shortcut. And related to that is an important rule is that please, when you're doing any of the problems, do not post solutions online. And why? It's because, well, why would you post solutions online? You're not actually helping anyone by doing that. And you're actually hurting people because it makes it possible for them to not struggle at something. Please don't, if you find someone doing it, please ask them to stop. And it's not because we need questions to grade people on, because there are no grades here. This is because we care about knowledge and mathematics. Okay, great. So maybe as we near the halfway point, and I want to get to mathematics for the second half. I just want to give one last thing, which I'll describe as maybe the parable of the musicians, which is maybe to lead up to it. I presume many of you have already noticed and know well that, let me first update this, that you've noticed something that like people go to college in the States and they get these very heavy, massive textbooks, and they feel very important because they're carrying heavy mathematics around. And yet, as the courses get more and more complicated, the books get thinner and thinner. And there's a reason for that. And that's because somehow the more you understand, the less you have to memorize. And then you can concentrate on memorizing the things that's really hard to memorize. And I had an epiphany at a very unusual dinner. It was unusual because, well, one reason is the host of the dinner at some point was firing a crossbow inside the room, which was quite memorable. But more memorable was a conversation I had with a couple who were professional musicians, and something which always I asked them something which I'd always wondered about, was when I studied music when I was younger at a very amateur level. When you learn a song, you'd memorize it. You'd know where all the pieces, you know where every single piece went. And it always blew me away, this very minor fact in all the things that professional musicians do, that very long pieces, they would not, like, how would you memorize an entire symphony? How would you memorize where you fit in with absolutely all the other instruments? And the answer was, in retrospect, really obvious, which is obviously they don't. And they know the music, they played it. And there's just a few key points. You remember, once you start with a certain phrasing, it just carries you on, and it's obvious what's next, and you do the rest. And I realized that it's exactly how we understand the world mathematically, which is, for example, in a proof, you don't memorize every line of a proof unless you're taking the tripos in Cambridge 100 years ago. That instead you just know how it starts and roughly the direction it goes, and that's enough to let you repeat it. In any proof that you can remember that way, you really remember. In any proof where you have to remember, oh, there's this one trick, that's a hard proof. That's a hard one to remember. That's one you don't understand as well as you think. So great. So now let me go to, now I would love to at some point pause and ask for questions, and the 20-second delay means that this does not work well. I don't know whether the shepherds have something they want to, if there's anything, we have no substance yet perhaps, but if there's a question or a comment.
I'll let you know when questions come up.
Great, okay. So normally it's a bad thing when questions don't come up, but I think given that there's no content yet. Okay, so now to the actual mathematics. I should say from the start that my point of view in algebraic geometry is not my own. It's inherited from many others. I think of it as, I guess, Joe Harris gave me a heart mathematically, Brendan Hassett gave me a brain, and Johan de Jong gave me a spine. And I probably learned the most.
Hey, Rafi, could you speak a little slower?
Sure, thanks. And I probably learned the most from people who were allegedly my students in one way or another. Okay, so good. The time is 8:30 here, which is so exactly where I want to be. And so the first thing I want to discuss is why you should care about algebraic geometry. And I don't want to say too much, because if you don't know, really, you probably shouldn't be here, because it's an important question, but it would take a long time. There are very, very many reasons to care. But I just want to say things that attracted me to the subject early on too. So here's a flavor of problem that you reasonably might have seen when you were small. You might have heard, so I guess Fermat's last theorem is something you hear about, and you're trying to show that there are no non-trivial integral solutions to something like this. And we know, thanks to Wiles and Taylor-Wiles, that it's true. And when you hear about this, you can't help but think about the case where it's false, where you have the question of Pythagorean triples. And with Pythagorean triples, so something is different for 2 than for 3 and up. That there are answers when n is 2, and there aren't answers when n is not 2. So with Pythagorean triples, you could try to find them all, and there's a very nice way of finding them, and you can describe it, depending on your point of view, in very different ways. And one way of doing it is by one perspective, and I guess they're all somehow equivalent, is to instead divide by, look for rational solutions to rational points that lie in a circle. And so now, just to emphasize, when you ask the question, you're looking for rational points on a circle, but you drew, I hope you would draw a circle, which are the real points. And so why did you do that? What advantage is there in writing down the real points? And the answer is, there are, of course, many advantages. It lets you think about this in a correct way. And perhaps if you've seen this before, and if not, this may come up later again, that one trick of getting all the rational solutions is noting that there is a single point that you can identify easily. 1 squared plus 0 squared is 1. And if you take any line through it, y equals mx minus 1, with rational slope, the other point will have to be rational. And conversely, if you take another point which is rational, you will get a line with rational slope. So you get this nice bijection between rational slopes and most of the points on the circle. So that's geometry, but it's also arithmetic. Now let me have it always add that. Okay, great. So that's so now how about x to the n plus y to the n equals z to the n? Well, you could graph that, and you can get something which looks, I don't know, like that probably. So you get something which looks like this. And so let us, so we're looking for rational points here and trying to see that there are only these 4 that are present. So what shall we do? So, and the old trick doesn't work. So what do we do? Well, here's a crazy thing to do, which is let's look for complex solutions instead. And there are lots of complex solutions. Again, let me just quickly go to u to the n plus v to the n equals 1. And so it turns out that the complex solution forms something that looks like it's a Riemann surface, except it's missing some points. It's missing endpoints, but that doesn't matter too much. And so on it, we have these 4 points. So in this complex picture, we have the real points, which are just kind of around here. I'll leave as a question as to how it interacts with these holes. And then the ones we actually care about, the rational points, of which there are only 4 secretly on it there. So how does it help us in this case to think about this curve and think about this Riemann surface. Well, there's this amazing conjecture, which is later a more amazing theorem, which is Falting's theorem. One of the uncountable number of fields metals that is done in the language of algebraic geometry, which says the following thing, which is you're interested in rational points. So you look at complex points instead. And if there is more than one hole, if the genus is bigger than one, so this is something about geometry, it's about topology, then there are finitely many rational points. And that's just weird because these points are nowhere near the holes. They have nothing really seemingly to do with them. So there's some magical, something very deep magical is going on that we knew for decades before Falting's appeared to be going on, and it's something linking the arithmetic, the geometry, the topology, and the algebra. So that's a flavor. And the Weil conjectures, I should not do something like that. Instead, the Weil conjectures are a different flavor that also show something miraculous. And just roughly to say, let me store that, roughly to say what the Weil conjectures are about, at least as an idea, if you have something in C to the n, and it's cut up by a bunch of equations, and let's say they have integer coefficients for what you'll see y, and so you've got something in C to the n which is cut out by, so we're inside, I can't draw C to the n, so I'll just do that. And you have this thing which is called a variety, and I can say this in a much more general way, but let me just say it this way. And this variety has some topology. It's got some different holes of different sizes. So that's about topology. And instead, what I could do is take these equations and I could just take the mod p. And when I take these mod p, then the integers mod p form a different field that looks very different, just p minus one element seemingly. And so I could just look for solutions mod p. So this picture is about looking for solutions over the complex numbers. And this is about just counting finite number solutions mod p. So, so in effect, what this is saying, what the Weil conjectures say is that by counting these solutions over finite fields of general sizes, you can actually then, that tells you about the holes, about the topology of the complex thing. And conversely, if you know the topology of the complex thing, it tells you about solving things mod p or in all sorts of other fields. So once again, something very continuous connects to something that's somehow very discrete. And then the very last example I'll give is if you've seen the Gauss-Bonnet theorem, or maybe you've heard of the Riemann-Roch theorem. And then so there's a whole bunch of things that grow up to be, on one hand, the Tia-Singer index theorem. And really, it all came from Grothendieck-Riemann-Roch, and which of course came from Grothendieck, not Riemann-Roch, and it was his ideas which made it clear what to do on this side as well. I'm not belittling the Tia and Singer by any means, of course, but what are these all about? It's about something discrete and something continuous being the same for no good reason. And so these are the kinds of things, these dramatic mingling of different parts that I find interesting. So and so maybe some themes we'll see soon are things like when you see the polynomials, you should think of this as being a smooth curve, and that's even true for polynomials over in one variable over an arbitrary field. But also when you see the integers, it's also a smooth curve. And what does that mean? Well, all sorts of things need to be made sense of, such as it's one-dimensional and it's smooth, and how do you even define those things, and what's the set, and things like that. And another thing is, what is projective space, which has many different answers, and somehow every single one opens up something deeper and deeper. Okay, so now I am ready for to actually get to some to category theory. Okay, so here's some categories for the thinking mathematician. And I should say what I want at the end of this, probably later today, or maybe if I'm too tired tomorrow, I'll put up some problems and some readings and aim them at people who know different things. So I'm hoping that people who've seen proofs already and think about modules will be able to comfortably read up to section 1.5 in the Rising Sea, but skip all the starred section. So anything starred is hard in the sense I described it, or at least we don't need it, even if it's not hard in some deeper sense. So, and in particular, if you're seeing this for the first time, the notion of universal properties is the fundamental lesson I want to get across today to people who haven't seen it. So, okay, so let me now quickly answer the question of why are categories? Why is abstract nonsense? And so, categories are supposed to be nothing more like any mathematical object. It's something, these are things you've seen before and we abstract away, and there's some value in doing that. So there are lots of parts of mathematics you've seen, like vector spaces. There are a bunch of vector spaces and there are linear maps between them, or there are sets and there are maps between them, or they're topological spaces and continuous maps. Basically, you have things and you have maps between them. And so these things can be vector spaces.
Ravi, some people are saying your handwriting is a little unclear.
That is, I would say that too. Let me try to be a bit more. This is a danger of having my original slides invisible. So let me, great. Actually, also, unfortunately, with the 20-second lag, it's bad. Let me know if things get particularly unclear. So what's a category? You've got a bunch of things, and we have to be fancy, so we don't call them things. We call them objects, and we don't have maps. We just call them morphisms. But you already know what they are. And what property do these things and maps have in all the examples you know? Well, you can compose two maps so long as the target of one map is the source of another. You also know that given an object, there's a notion of an identity map. If it's a vector space, it's identity matrix. If it's R to the n, it's identity matrix. If it's a set, it sends every element of the set to itself. You also know that when you compose, so you have this information, and you also know that when you have three maps in a row, that if you compose these two, and then that one, it's the same as composing this one, and then the composition of these two. So those are, you can write them down as axioms. And if you, there are all these foundational questions in set theory, which I will ignore. If you want, you can not ignore them. I feel like you should only not ignore them when you really want to not ignore them, or you will never come back from beginning that. So that's basically what a category is. And now, and what you should do if you haven't seen categories before, to emphasize that there's nothing new, just write down as many categories that you already are friends with. But as soon as you make the notion of a category, you automatically have the notion of an isomorphism, which is between two objects, which is you have two objects, and isomorphism is a map from one to the other, and there must be an inverse map. So the combination of these two should be the identity on this one, and the combination of these two in the other direction should be the identity here. So you already know what an isomorphism is. That's nothing new. And you have the notion of an automorphism and maybe an endomorphism. And as a good test, a really parsimonious definition of group is a group is basically a category, not basically. You could basically define it as a category with one object, and all morphisms are isomorphisms. And that's why, is this the best definition of a group? I would say in one metric, it is the best definition of a group. And another metric, it is so much the wrong definition, it's not funny. Okay, so now comes the examples I want to do that, which is the first example is that of products, and then moduli spaces, And then both of these are going to be examples of universal properties. And that will be, oops, not universities. And then that's where I'll end unless I informally define a sheaf for you too. Okay, so, okay, now what I'm about to say, this is called abstract nonsense for good reason, but I don't want your eyes to glaze over. And if you've seen this, you've not seen this before, you're going to be tempted to think that you'll just read it later. But it's the thing about it is actually really not hard. It just is, it just changes the way in which you see the entire world. So the first example is that notion of a product. And when I say product, what do I mean products of? Well, you know lots of examples of products early in life. So you know about products of sets. I mean, even products of numbers comes from your idea of products of sets. And you know about products of vector spaces, products of groups, and products of, if you have you should have an intuitive idea of what a manifold is. You don't need to know a precise definition, but you then realize you have an idea what a product of manifolds is. And I want to point out that when at some point people are just calling them products, and what right you should be complaining, what right do they have of calling them products? One possible answer might be that, well, maybe it's often they're product sets and they have some additional structure, but that's not a great answer. They deserve the name product because they have something even better in common. And so let me describe what that thing is. So if you have two sets, U and V, and just to let you know where I'm going to go with this, I'm going to later on say that everything exactly the same with vector spaces or groups, then I will define something called U cross V. And so what is this thing? Well, I'll tell you, I'll define it in the following way. And it's something which is going to have maps to U and to V. And this is the thing which I'm going to call the product, not just this thing here, but also with the maps to U and V. Okay, that's not yet a definition. So here's something which is almost a definition, which is if you have anything that has a map to U and a map to V, then there's a map to the product. And better yet, it's unique. There's a unique map that through which this factors. So the map to V is this followed by projection. The map to U is the map to U is this followed by that projection. Oh, you might as well call these projections. So I claim that's my definition, and it's that's a really good definition. And you might think of, okay, for sets, you know what this is? This is supposed to be ordered pairs. And for sure, if you have a set mapping to one set and another set, you do get a map to the set of ordered pairs. So far, so good. But then I tell you that my notion of product of sets is not yours. In fact, I don't write them as ordered pairs. I write them in the following way, as things, as a U on top of a V, like that, where little u is in capital U and little v is in capital V. That's my notion of a product. It's like some sort of strange vector thing. And you write it this way. And I say, that's my product. And you will likely say quickly that, well, that's dumb because obviously ours are the same, really have the same information. But let me just make it more, rather than waving hands, let me say the following thing, which is you have your product and I've got my product, which I call, I don't know, I'll call it that thing here. And so I claim that mine, I know yours satisfies this and mine satisfies this. Now, this is why they are the same. So, so yours comes with a map to U and V, and mine comes with a map to U and V. And by your universal property, I know that anything mapping to U and V, such as that, such as mine, that's exactly the same. That information is, there's a unique map like this that makes this diagram commute, that makes these triangles, that factors this into this and factors this into this. And similarly, if we trade places, there's a unique map from yours to mine because mine satisfies a universal property that that makes everything commute as well. And when I when I combine yours and mine to get a map from mine to myself, or I could do the same thing from yours to yourself, I claim this is the identity. Why is that? Well, here's the maybe bizarre thing. Use the universal property on you, on mine, with it and itself. The first map to U and V is the one I actually started with. And the second is by going through the magic mirror and doing it on your side. So the identity map, there's an identity map that makes, and there's also this map, which makes everything commute. And because by universal property, there's one and only one map from my space to itself, making it commute, then this combination must be the identity. So these two must be isomorphic. So there's just no way the first time you hear it, you don't find that incredibly confusing. This is the sort of thing you cannot say out loud without people laughing at you. But you have to think it through while you're walking around and realize that in some sense, there's nothing really there once you think about it the right way. And the advantage of thinking about it the right way now is I can now define products of manifolds. And I would say exactly the same thing, or products of rings or products of groups, and I've got the same definition. And the only problem with this is it's not exactly a definition, because here we have, in this example, two different things which deserve the name product, but they are isomorphic. They're not just isomorphic, they are canonically isomorphic. There's one choice of isomorphism that makes this work. So no matter if someone else a third person turns up with a different product, as long as they satisfy that universal property, we know not that they are the same as ours in a really strong sense, that there's a unique isomorphism between ours and theirs. So that's the single most important example to figure out if you did not understand it. Okay, so now let me try one more. Let me first of all make sure this is saved, and great. So now comes the notion of a moduli space. And I don't know who to credit this to other than generically Grothendieck.
Sorry, some people are saying sometimes you point to things and the pointer doesn't track, seems to be happening.
Yes, that is because I'm pointing with my pencil and you cannot see my pencil on the screen. That is a very good point. Let me see whether, now that, of course, the downside is, let me maybe restate this and see if this helps. Is that just going to be a lost cause? Let me
There's a laser pointer using notability, right?
I am, and I could definitely do this. But the main problem is I have to remember to do it.
Okay.
I think just in the future, it's probably a good idea.
Sadly, the problem of remembering to do it is not going to be it will remain a problem. But please remind me when I do it. So there we go. Now I'm remembering when it's not so needed. Okay. So the notion of a moduli space, I want to point out things you already know, which is if you wanted to say what are the circles in the plane, then you might quickly say, well, okay, they're things of the form. You might write them down like this. And so they're parameterized by two real numbers and one positive number. So that they're parameterized by, I guess, R cross R plus positive real numbers. So we know in some sense there's a natural space. So there's not just a set of circles. We naturally think of it as a manifold or something much better. Similarly, if I said about projective space, let me talk about RP or RP2. And now I would like to do something visual, but I don't know. I have to, while not looking at what you can see, I will just attempt to stare into the camera and see if I can make this work. So what is RP2? Well, one possible answer is you think about 3 space, which we, to first approximation, live in, and we consider the set of lines through the origin in 3 space. Now I'll put this down. Now I really am using my pencil and forget, I'll ignore that part. So the points in projective space correspond to lines through the origin. And when you say it this way, you can believe that it's not just a set of lines through the origin. Like there are 2 degrees of freedom. RP2 is 2-dimensional. And so that's a point in projective space. That's a path in projective space. This is a loop in projective space. This is a non-contractible loop in projective space. That something is telling us that we have a notion, not just of this as a set, but as something better. So now let me take us to Riemann. So let's say we wanted to consider Riemann surfaces. You don't need to know precisely what these are. other than their complex surfaces. And you can't read that, I know. And this one has 3 holes, which means the genus is 3. And then it turns out that there is a nice notion of a space of such things. Now, what does that possibly mean? Well, the space, which is called M3, and now people will know that some people will know that I'm lying, but they will also know that I'm not lying in a, it's actually a fairly serious lie, but it's a lie because I have your best interests at heart. So, so we have a moduli space of such things. What do we mean by that? Well, this thing is basically a manifold. It's actually an orbifold, and we'll worry about that much later, if ever. But what does it mean? Well, you have the set of such curves, such Riemann surfaces, and it's just a set. So why does it deserve to have the name of a manifold? Well, the answer is, if there is such a space, what it should mean is that anytime I have a family of such curves, let me just describe it. So I've got, anytime I write some family of such Riemann surfaces like that. What do I mean by family? Well, we need to make that make sense later on. We have some nice family of Riemann surfaces. Then to every point down here, there should be a corresponding Riemann surface. So there should be a point in this thing, which might just start off being a set. So in other words, the families correspond to maps to this thing here. And now that means that we have defined what this thing is up to unique isomorphism by exactly the same argument. There's one and only one such thing that satisfies this property up to unique isomorphism, assuming it exists, with the big caveat that if it exists, if something satisfies the property, it is unique up to unique isomorphism. In other words, that means that we have every right to call this a manifold. There's one, it's not just a set, it's something which is actually a manifold. Sadly, it doesn't exist. So that's part of the, that can make you sad, but it can later make you happy too. Okay, so let me, so these are both examples of constructions by universal, of things defined by universal property. In all of these cases, what you need to do is show that it actually, you have to show what it is by universal property and then show that it exists. And once you've done that, the universal property can actually be a huge help. So in the last few minutes, what I think I would like to do is to quickly say what a sheaf is, mainly to seed your mind for in the future, to convince you that this is not a scary notion. So and then just to conclude by wondering where things go from here. So maybe let me start with the notion of a sheaf. And so what is a sheaf, or why is a sheaf? What I'm instead going to do is tell you examples of sheaves, and then we'll later next week abstract what we mean by that. So here's an example. So consider some nice space, maybe a manifold, or I think something really concrete, like the desktop in front of you. And so my question is going to be about continuous functions. Let's do continuous functions on X. But I don't want to have, but I want to think about it in a really better sense. I want the information of continuous functions on all of X, there's X, but also on any open subset of X. And so let me call the continuous functions, let me call, this is an O of U, to be the continuous functions on U. And I'm going to observe that a bunch of things which are just obviously true. First, this is a ring. You can take two continuous functions on U, you can add them, you can multiply them, you can subtract them. So it's definitely a ring. Secondly, let me save this. Secondly, that if we have, there's X again, in case you didn't remember it. If you have a continuous function on U and you have a smaller open set, you can restrict a function on U to the smaller open set. In other words, there's a map of rings that's a restriction map from U to V. And furthermore, if you had an even smaller open set, you could restrict to V, take a continuous function on the big open set and restrict it and restrict it. Or you could restrict it all at once and you get the same thing. So this says that this diagram commutes. So these are all obvious things about continuous functions. Now there are two further things which are also obvious, but actually have a somewhat different flavor, which is the following thing, which is that if you take X and I have an open set and I cover it by a bunch of other smaller open sets and they cover U. And let's say I have two functions on U, two continuous functions. And let's say they are the same on each open set. The restriction to each open set are the same. Well, then they must have been the same function on U to begin with. That's clear because that's how functions work. And similarly, if you have functions, I'm just going to say this in words. Similarly, if you have functions on each of these smaller open sets, and they agree, if the function on this one and the function on this one agrees on the overlap, we can glue them all together to make a single function on the big open set. So in other words, the function, if you have functions locally and they glue together, they agree on the overlaps, then they come from something on all of you. So that, I'm just stating obvious facts about continuous functions. And now I will tell you obvious facts about differentiable functions, which is, let me call all of you sloppily the differentiable functions on an open set. Or if you want C infinity or something else, then you can restrict them to smaller open sets. And if you have differentiable function, two differentiable functions on U, and they restrict to the same functions on each things in a cover, then they must be in the same differentiable function. And finally, they glue together well. And the same is true with, I don't know, C infinity functions, take your pick. And so that's some commonality in all these cases of things that look like functions. And so that is, so I've not defined a sheaf at all, and I'm not going to, but I've just made some observations. So let me now finally just sum up by saying we're at we've reached the hour mark, and this is intended not to summarize or be a week's worth of things, but to set people up collectively for a week, and it will be a different week for different people. So what comes next and what happens next week? Well, next week, I know mathematically roughly where I want to go, but how this is going to work for us collectively, I have ideas, but I'm not actually sure. And a lot will depend on what happens with you collectively as well. So if you, so essentially I want as many people as possible to be thinking about things at the level that's right for them to push the envelope of their understanding. If someone is near the edge and falling off because of they're just barely holding on, then reach out. I bet we can actually, we'll try to keep you on. Or if it's too much, that's quite okay too. And if you are a fancy person, you should also be looking for interesting things. I'll try to give you interesting things to think about. And if in doubt, you can always look to the very, there's some rather amazing senior mathematicians who are, quote, participating, and you should ask yourself what they're getting out of it. And it's something different, but it's something non-trivial. So now I think probably I will defer to the shepherds a little bit, but now might be a good time to end the recording, although I guess we'll keep YouTube on, but later on we'll cut the recording here and we can do a postmortem. And I don't know whether questions, philosophical questions, isn't so much in the way of mathematical questions that you might have just yet. And then I can hang around for another half hour. So great, so let me ask the shepherds. Is that a good plan?
Yeah, that sounds good.
Great. Okay. Thank you for the clap. Great. So I will, let me keep the screen sharing. Let me end the recording on Zoom. Actually, I don't know how to do that easily. Well, who cares? And so so you can all head off into the sunset, but if there are questions.
You're getting a lot of thank yous in the YouTube chat, by the way. So
thank you. You're welcome. And I'm wondering, maybe so we can have up to 100 people on Zoom. We could just put the Zoom link there and people can join and ask questions, or is that might be easier than doing Zulip?
So you can't, we can't post links into YouTube.
We can post them into Zulip.
Yeah, into Zulip we can.
Okay, do you want to put the Zoom? Should I get that? And okay, and maybe I will stop sharing so I can see people. Stop share. And good. I see people have managed to get in who did not otherwise couldn't see things. I'm happy because I wanted that to be the case. And great. Do on Zulip, is it already available? Is it easy to find for? There it is. I sent it to Long Fei. Let me. Let's see. What should I do? Should I send it to the shepherds? Is that and then I could try to. I can say it in every group.
I mean, you just post it in the main chat. The main lobby.
Great.
Why not?
Yep.
Or I can do that if you want. I already copied it. If you.
You already did it. Okay. Well, maybe you already.
No, I didn't do it yet. But we didn't need a password when we went in, so I'm kind of concerned about that. Like
that should be okay. And I should say that because this is it's only sort of public. It's not fully public. That we should be. We're kind of counting on people not being jerks and Zoom bombing.
Okay. I guess it's in the Zulip. Since we're putting it in the Zulip, it'll probably be fine. Yeah.
And if it's a problem, we won't do this ever again. We won't do this again.
All right, let's.
Great. Okay, so people are actually coming in, and the good thing is other people can watch still on.
Quickly, it looks like.
On YouTube too. Okay, great. I don't know how we should do questions because there might be enough people. Like it might be enough that just shouting out might not be good, but.
Why don't we try it?
Yeah, that's right. Yeah, let's try. Yeah. So maybe. Raise hand. Yeah, raise hands for questions. Oh, sorry. So there's a question from Jack. I was not looking at.
We gotta manage the waiting room too.
Yeah. Great. I'm just admitting everyone, clicking admit all the time. So call out ahead. Any questions and I should say this also includes how we should do this. Like how we should do this in future weeks too. Maybe on Zoom we'll talk about that.
I have a question, Ravi.
Sure, fire away.
So how did Riemann think about the moduli space of curves? So
that's a good question. My guess, my extracted answer from hearing other people and making guesses is that he knew the space. He could see, like, how do we know the dimension of a manifold? One way of thinking about it is you might say it's degrees of freedom when you take something and try to move it. So he knew somehow that he knew there are 3G minus 3 complex degrees of freedom. So he thought of it sort of as a manifold, but it wasn't, but it's a good question. Like the notion of a manifold did not exist then, let alone orbifold.
Mm-hmm.
So
I think he had moving branch points or something for.
Yep. So he can count dimensions that way. And actually, you can actually get the dimension of mg that way in a nice way in modern language too. But he really knew what he was. Yeah, it's a strange thing that he really knew what he was talking about without having the modern words to say. And I guess he was doing it. Yeah, modular forms. They were doing.
Another question that's.
Yep. Another question.
Yeah, Emily Real asks, can you say more about the lies involved in the moduli space of Riemann surfaces, even if the answer includes words we don't know yet?
Sure. So let me say the lies in a truthful way. I mean, I could just quickly say it's a stack, it's an orbifold, but really the correct thing to say is, okay, it's not a manifold. You try to, and what do I mean by that? Well, I mean that you can't, I said what the universal property was, but there is no such thing. There's no manifold that satisfies that universal property. And so the question then is, what do you do? Do you just give up and go home? And version 1 is to do what Riemann did and just never really ask the question. Version 2 is to try to get something manifold-like, which kind of best approximates it and have some variety. And Mumford got his Fields Medal for using geometric invariant theory, developing that to give the sense of that. But really the right answer, which Emily actually knows, she's probably the single person here who would know this well is that you make the right notion of, you want to say it wants to be a manifold. It's not a manifold, it wants to be a manifold. So you need to define a new kind of space to make it make sense. And this new kind of space ends when you figure out what it wants to mean is the notion of a stack. And maybe I will say that the definition of a stack, one lie that people tell you is that stacks are complicated. And stacks are absolutely not complicated, more complicated than sheaves. Delene buffered stacks can be, some things can end up being complicated, but I could define a stack fairly soon after defining a sheaf. And maybe I will next week to try to convince people that that's actually true. A stack is basically like a sheaf plus one. It's like a one more complicated thing than a sheaf, which also relates to, I guess there's like a question Jack mentioned, universal property. It's a good one here. Some of these are really easy. Right, giving up things in the local to global properties of the sheaf's definition. So you have to give up the right thing. And so here's a philosophical question, which is the one which is logically prior to the other, or put differently.
Could you repeat the question? I think not everybody sees the chat.
Sure. Oh yeah, sorry. The question is, I have to find it again. In the definition of sheaf, which I also didn't give, but when there are these two local to global properties and you give one up. So let me ask the question in a different way that doesn't refer to that, which is often in math, there's you often see things of statements where there exists a unique blah, 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 blah. And these are so important phrases that we have these symbols of backwards E's and exclamation marks to summarize what they are. So you always see there exists a unique, and the question is which one of those two is more fundamental? And if you know that, if you figure that out, then in fact you realize that there's a first, there's a second, but then there's a third and a fourth and a fifth and so forth. And then you're in Emily Real fairly quickly. So that's the to help set that up. Oh, I should say separately, I was chairing, because that's how the weird way Stanford works is, I was the university chair of a PhD defense in philosophy last week, in which it was actually really, it was really cool. But the speaker was talking about how, I think it was Frege, was thinking about existence and uniqueness, and he thought about one in terms of time and the other in terms of space. And this was very strange that he would think of them as something different. And I feel like the philosophers knew this, and we know this, but Frege did not know this. So, okay, I didn't even answer that question. Great. Yes. Let me state and answer some things really quickly. Defining stacks right after defining sheaves. Okay, I'm willing to do that, but I will not do that in the hour. I'll do it I'll do it on the side because it's completely, if you haven't seen a sheaf, then seeing a stack will either hurt your head or give you the wrong idea, and you might get infatuated. So, okay, maybe next week I'll define what a stack is. Secondly, in the definition of a sheaf, make clear why, just quick feedback on make clear why partially defined functions, that is, the rest of it is a good question. And I will deliberately duck that for 1 week because I was somewhat deliberately imprecise because I wanted to say something and I didn't want to say everything. So let that sink in your head for a little bit, and then next week we'll talk about that. Great. I didn't understand how a family Riemann surface defines a map to M3. Well, that's because I didn't really say what M3 was. I'm sorry. Really what I mean to say, what is M3? It is the hypothetical dreamed of space of all genus 3 Riemann surfaces. In other words, I'll tell you the points of the space. You give me a genus 3 Riemann surface, I'll give you a point of the space. You give me two that are isomorphic, that are the same, that's the same point. You give me two that are different, I'll give you two different points. So far, I've described just a set of genus 3 curves, but I'm claiming it's something better, except that, of course, I'm lying. I'm claiming that it wants to be a manifold of a certain dimension. But what right do I have to give it a manifold structure? The answer is, and this is the thing, which is a one-line sentence, but it takes a long time to digest, which is if there were a manifold of genus 3 curve, parameterizing them, then here's your manifold. I know you can see my hands, or there's your manifold, and over it you've got each genus 3 curve, they fit together nicely in some family, whatever that means. It's like a product. It's a bigger manifold, and the fibers are all genus 3 curves. So I'm not making this rigorous, but I'm making it something that you could imagine you could make rigorous. And so that should be, in every genus 3 curve, they should fit nicely together in this family. So what happens if I have another family of genus 3 curves, not this best one? The answer is, if you've got a family of genus 3 curves, then for every point in your family in the corresponding to one of your curves, that should give me a point over in my moduli space. And so this should give me a map of sets from your parametrizing space of your genus 3 curves to this thing here. And this better be a map of manifolds. So that's at least something I can, if you think about it in the case of circles, it's something, an example of circles, it should reasonably be a map of manifolds. And then if I say, okay, great, that's my definition of moduli space. I'm not telling, this is not a theorem that the moduli space has this property. This is a definition of what moduli space means. And it's like this huge light bulb kind of explodes in your head when you realize that that is, if you try to define it any other way, you cannot. You'll say something imperfect, and that this is forced to be your definition. So that was the expansion of the universal. Oh, Jonathan, you said there's an expansion of universal property. Was I vaguely trying to do that?
Yeah, I think it was the same question.
Good. Okay, great. And then, great. Okay, good. And I'm also go backwards a bit. The why math question, I should say that is a long answer, and I think there's like a really super good answer as to why math kind of rules the world, but that's and why, in particular, thinking abstractly and theoretically has guided human progress for millennia. But that's a much longer one. I did not explain what a universal property was. That is true. So that's not a question. It's a statement, but it's a true statement that I did not explain what a universal property is. So you can read about that, and I could say it, but it's something you have to actually, that's why this phrase abstract nonsense is there. I could write it down, and you will kind of look at the symbols on the page. But let me describe it this way in an imprecise way, but I really do think about it this way, which is, if you know the maps to something, you really know the something. And I often think about this in a physics way. You've got some, okay, this is horrific in terms of actual explanation, but you take like you have some, a physical object you understand. So you put it in your, I don't know, your linear accelerator, and you like shoot things at it. And by shooting things at it and seeing what happens when you hit it, you understand what that thing is. And that's just, as a metaphor, it's horrible, but as a picture, I like it. And so what this is saying is that I know, like, what is the product of two things? Well, you could define it with ordered pairs. But that's kind of, I would, only you've been brainwashed into thinking that's a reasonable thing to do, right? I mean, why would you, probably the reason you were brainwashed is someone drew a picture of a product. You said, oh yes, that looks like a product. And then you realize, okay, that's ordered pairs and used Cartesian coordinates or something. But you have to realize that came second. That was not what came first was your picture. So what does universal property say? It says that you know an object by knowing all the maps to it. You know M3 by knowing all the maps to it, which means you know all the families of genus 3 surfaces. And so if you know that, that will tell you exactly what that alleged space is. Admittedly, it may not exist, but if it exists, you know it up to unique isomorph, up to, like, you know it in all the sense that matters. But then that's not a rigorous definition at all. So, but you have to read it and meditate on it for a long time to realize that that's what it's saying. Great. Here's a good one. Are we still using Discord for anything? And nothing really. It's just we'll see what we end up using. Currently, I would say nothing too much, although people are asking some questions there. Maybe some groups will want to work there. Up to them. I feel like we're going to find out what's useful by just watching what people use. Oh, a great question from Quinn. Quinn asks, raise hands for questions, ? And I think that is, I would say, sure, if you feel like it. And Jackson, I had that for a while. I don't. Oh, high pitch ringing. Yes, that is, that high pitch ringing was the leaf blower outside. One person says he's talking too fast. I was the one saying that. I'm too scared of Zoom and strangers. I don't even know what that's about, but I'm scared of strangers. Oh, a great question. Yep. Your questions, ? And I think that is, I would say, sure, if you feel like it. And, oh, what's that? I missed that a little bit. Can you say it again? How do you know who's talking? Okay, someone said something brilliant. I don't know who it was, and maybe it was a Zoom bomber who just came in and said something quickly about it.
Somebody's asking, Rachel is asking, how do you know when you've picked the right universal property? Oh, wait, Emily Real just posted an answer as soon as I said that. Okay, never mind.
Yes.
Okay.
Okay, first thing, let me quickly read this. Actually, one thing I would like to say, someone has their hand raised. Actually, about Emily's answer, if you can see it in chat. Oh, it's gone. So let's see. Actually, something which interests me very much in her answer is the "some people, though not me," which says that represents or co-represents. I think I kind of know I would agree with whatever she's saying, but I'm not sure what she's saying with the "not me," why that represents or co-represents. Yeah, actually, maybe could you say that? Where is she?
I just don't think it's. I mean, this is not an important point. I just don't think it's necessary to distinguish between whether it's covariant or contravariant, because from context, it's always clear. So.
Right. Okay. Right. I feel these are sort of important because naming really does. It can be more confusing to say things.
You want to say in my chat, I'm getting the same kind of questions too about representability. You know, I mean, this kind of theme is coming up as well. So. Right.
Oh, yeah, right. How do you know when you have the right universal property? So, okay. So now you're asking an art, not a science question, which is what is it you're trying to talk about? And I'm not saying this flippantly, because often people try to talk about something and have different, realize they mean slightly different things and have different universal properties. And then they may end up being the same thing, or in Emily's phrase, representing, they may be representable by the same object, but really they are the same moduli space, or they may not. So the answer is, that's how you kind of do, it's like, I don't know, you, in physics, at some point we realized that mass and weight were not the same thing. And they started off as the same notion until, I guess, Newton probably. And then we realized that the notions were, that we wanted to disentangle them. So the answer is, it depends on what you want to, like, what's right, mass or weight? And the answer is, depends what you are using it for. Great. And then someone asked, is it possible to keep the half-hour discussion? I guess awkwardly, part of the promise was not keeping it because that way people felt comfortable asking dumber questions, because I don't believe there are dumber questions. You're welcome to Rachel. And to Itamar, I don't speak that language, I think, so I'm not sure what that says. But maybe I should say I'm happy repeating anything. And other people, I should say, like, there's a lot of other people here who would say broadly similar things, except with maybe philosophically different points. Someone with their hand raised. Let me just go and whoever has their hand raised can go just say something. So there's a lot of different.
Yes, I wanted to ask, what is so universal about universal properties?
It is so why the word universal? I think the answer is this, but someone can correct me if I'm wrong, that it's among all the, what is it about the product that makes it special? Well, it's special among all the things with maps to U and V. It's universal in that it has this one property that for anything that maps to U and V, it factors uniquely through U cross V. It's like the property which defines it. I don't know if that's convincing or not, but that's the that seems to. Yeah, Jonathan's looking alarmed.
Thank you.
You're right. Great. And I should say, like, the thing with universal properties, one thing you should do if you haven't seen them before, which is it really is revelatory. Like, there's this thing called Yoneda's lemma, which has no content, but it's in some sense, but it's very confusing as well. So first, like, it's really important you do exercises involving universal properties. And then I should say at some point later on, there's something you want to prove. And you could prove it, everyone proves it by doing something with actual concrete things. And then someone else who here had a one-line argument by universal property. And I think looking at Jonathan Wise is someone who's notorious for having one-line arguments like that other people spend pages on, and you hear that and you suddenly, your mind is blown. And then the very first time you yourself write down an argument that is universal properties, by universal property, you just, like, your life changes. Like you feel like your life is, like that should be on your bucket list, because you just suddenly realize, wait, that's just so simple. Oh yes. A sheaf, someone said, a stack is like a sheaf plus. And right, no, in fact, that's all I said. It's like, so there's like a sheaf, there's a notion of a sheaf, which has these two properties, which people have mentioned, which I'll say more precisely next time, the identity and gluability property. A stack has, in some sense, three. But the best way to think about it, and now Jonathan's going to get upset with me when I say this, is great, because I can, no, sadly he's unmuted, so he can actually argue. But the best thing to do is to not give the definition. Yes, plus a triple overlap condition, indeed. But to instead just point out some examples you already know of stacks. And then the fact you already know them and you just observe they satisfy something, obviously. And then you realize, wait, that's a thing. That thing deserves a name. Stack is a stupid name, but I guess sheaf is there are a lot of stupid names. Sheaf is actually reasonable, I think, once you realize what they're thinking. I don't know what they're thinking with stack. I don't know who came up with stack. That's the French would have said, wouldn't have used stack. Maybe it's a mistranslation of the French. I mean, yeah. I blame Jonathan. He's great. Are there sheaves plus two that we care about? Ooh. No. Well, I can answer that. That we care about? We, first person plural? No, I don't think so. But are there sheaves that people care about? Yes, definitely. That come up in useful ways. Field is taken. That is true. Okay, Jonathan Wise says translating CHAMPS as field. That was taken. So they had to pick a stupid name. Like they could pick lobster. I don't know. Pick something else. Non-linear tour to the rising sea. Yeah, it'll be roughly linear, but the non-linearity is because this group is so heterogeneous that to say some, I think there are things that are interesting that can be said to different people at different times. And so most people can ignore stacks, even in what I'm saying. But some people are very happy with categories already, and they've seen this before, and maybe they are curious about stacks. So the tricky thing that I need to figure out is sort of how to make things interesting for as many people as possible. Oh yeah, Emily says there's no quote right universal property. Absolutely. Override. Yep, I can't really. Hopefully next time I'll be able to have slides available in advance that are accessible. And I think I am. Oh, maybe the last thing I'll say while Emily is actually here as well, that the history of the subject, like the revolution in algebraic geometry, happened not coincidentally after the revolution in topology. That somehow the language, Serre was a topologist before. His Fields medal was for topology, and so it's this clean way of thinking that was I think in topology first, and then once people were thinking cleanly, you just can't help but start to think cleanly about geometry as well. So that's why I didn't realize this until later in life, because I guess algebraic geometry for me was big machinery that people will tell you about, like very heavy, threatening industrial grade machinery. Whereas I guess I always thought of algebraic geometry when I first learned about it as being this very technical, hard, narrow, deep subject. And instead, I think it's what's hard about it is that it's extremely shallow and broad. That somehow it's like there's many things happening simultaneously. And that was the initial vision of it by Grothendieck. And it's people trying to understand him that and trying to collect their thoughts that made it unaesthetic. And it was like you're taking something organic and naturally growing and trying to turn it into something mechanical. And then you just can't help but have something like, I don't know, I feel like I'm gonna make a Terminator analogy at some point. So I'll just stop. Can properties locally be, I don't understand exactly the question, but can properties locally be global properties? I think if that question were to be made precise, it might evaporate and become, the answer might be clearly yes or clearly no. Good intro reference for moduli spaces / stacks. I can answer that question. No, I don't think there's a good intro reference for moduli spaces / stacks. I don't know, does anyone else want to argue with that? Is there a good reference? Anyone know of a good reference for moduli spaces and stacks? Nope. Okay, that's I didn't mean to be too aggressive. Yeah, read NLab till you give up on it. I think NLab is great. Oh, FGA Explained is fantastic. I'm not sure I would direct people first there. I feel like FGA Explained is fantastic. Moduli Curves is a great book, but maybe not precise. Like if you really want to know what a stack, actually, if you go to Moduli Curves and look for stacks, you will see the phrase, is it fat chance? Is that the phrase? Yeah, okay, Taylor's saying nodding yes. So yes, go look up the definition of stack in Moduli Curves. Intersection theory of Fulton has no stacks. In fact, intersection theory on stacks, oh, here's a good place for stacks a little bit, which is Angelo Vistoli's PhD thesis was about intersection theory on stacks. So he has an Inventiones paper, which is from his thesis in 1989. And the appendix is like a 3-page introduction to stacks, which is very Vistoli-esque, but it is actually beautiful. But then that's why I said Arth mentions in FGA Explained, it's a good, I do think we're getting a bit aside here. And maybe actually Jared Alper and I might at some point on the sideways say something about this, but I think I have an argument with the conventional description of stacks, I think, because I think the category fibered and groupoids is a terrible word. And it's just various things in the definition are kind of a crime against mathematics. But the actual discussion in, Martin Olson's X about stacks. I will put like a double, yeah, is fantastic. And Vistoli's notes. Yes, the deformation theory summer school. Yeah, right. So allegedly there's going to be a book there. Oh, also Fulton et al. Have a great introductory book, half which is introductory, which no one is ever going to know about because it of the impossibility of having a good book on stacks. So it crashed and burned.
Oh, Rob, if I could butt in for a second, can I suggest reading the questions on the Zoom chat for the YouTube audience?
Yes, right now I'm still talking about stacks. But let me go and read. Oh, good point. Sorry, for the YouTube audience, they'll have no idea what I'm talking about. Thank you. Thanks, David. Are universal properties sort of related to things like topological properties? Is it about invariance, or should I just keep these notions out of my mind? I would think of universal. I would say, okay, let me make them related in a certain way. Which is if you have a genus 3 Riemann surface, and I have one, how would we tell if they're different? How do we tell if they're different points of the moduli space? We would look for various invariants in order to figure out what they were. So when Mumford tried to make sense of this space, geometric invariant theory is exactly a way of finding invariants to make sense of these spaces. So it's related, but universal properties are kind of a better, I think are like the more fundamental notion. Landsberg.com. Oh, McClarty. I have no idea what McClarty's reference is about, but anything he does, is like really interesting. He's not a mathematician, but he's I guess, philosopher of mathematics or a historian, but he really knows his stuff and is interesting.
I've got a question from a slightly different direction, if that's okay.
Sure, yes.
So as an undergraduate, I read about things like Grosvenor bases and elimination ideals under the name algebraic geometry, and I've been sort of wondering what stacks or sheaves had to do with any of that.
So both, let's see, Grosvenor bases and, oh, I've already forgotten. What was the other thing?
Elimination ideals.
Right. So,
for systems of polynomials.
So they are transverse in the following sense, which is they are about, they are local. They're about rings. So elimination theory is about, you have a bunch of equations, you're wondering what's the condition on them for them to have solutions. So these are statements about rings. And so this is the algebra part of algebraic geometry. And then the geometry part are the things where you glue them, the global part, which is, and so elimination theory, other Grosvenor bases, there's like you can describe things so elimination theory grows up to being algorithmic ways of understanding images of maps. And then Grosvenor bases similarly grows up to be some sort of flat degenerate, the ways would be flat degenerations. So the answer is they are things that existed before modern algebraic geometry in both cases, but that are fully digested into it. Grosvenor bases is a bit weird because Grosvenor bases, they're weird because they were defined in a pure in pure mathematics, and no one really noticed them. And then the applied mathematicians realized they could do things with them, and then the pure mathematicians realized they could actually, that if you algorithmically understand something, you could prove theorems with them. And so somehow, I don't know what world, that's a good thing that pure and applied doesn't really, it's hard to distinguish. And if you get too hung up on it, then you miss out on things.
It's certainly true. So then proceeding in the direction of modern algebraic geometry then doesn't necessarily lead to better algorithms for solving systems of polynomials or anything like that.
It does, in the sense that modern computer algebra programs, which I guess the one thing, I don't know why, I think there are like cultural reasons why they tend to be, the advances are in Europe. I think because of the way funding works, that somehow things that cross disciplines are cut up differently in Europe than in the US. But they all they wouldn't necessarily use, they wouldn't use stacks in what they're talking about, but they would use, there are a whole bunch of things, much of topology in its modern sense is post-Grothendieck. So as well, we all live in the world of, like, commutative algebra is now done, even though that's all local in some sense. That's like not global. Everything is post the revolution. So I guess modern algebraic geometry is maybe the part of the inheritance that's really algebraic and geometric, whereas there's a different part that's algebraic, there's parts that's computational, and the leaking into computational things is slower because of the startup, of the difference of cultures.
Mm-hmm. I see, okay. Very interesting.
Great, so let's see, I've got Taylor, connected components of Hilbert schemes, parameters, great. Oops, I'm not sure what Taylor's oops is about, but maybe he's answering to something. Great. Actually, a lot of good. Oh, Google Grothendieck OpenNut, yes, that's that is
My oops was, I said connected components instead of irreducible components.
Oh, I see, great. Great.
Yeah.
Okay, other random things, and then I guess we can continue the discussion. Oh, and of course there is one person waiting. I hope she was not waiting a long time. But... Okay, cool. Well, question before, sorry. Patch set from Sol. I would say that's even more than I want. Okay, sorry, I should read the question. It seemed like the main take-home point from what I was saying about sheaves was that the patch set of small functions was the same as a big function. So I should say you extracted that from what I said. I didn't say that, but you're completely right. And is there a more important take-home point? I think the take-home points will be like, that's great. If you had that idea in your head from what I said, then I feel like then I'm happy. That's that. We'll talk about them in more detail. I mean, again, I didn't even define them, but the fact that they're in your head, in your subconscious over the next week, I think is a good thing, because that means that when you see them again next week, it won't be coming out of nowhere. Yeah, it's great if you find yourself wondering if you have questions like this in your head, then that just, I feel like, is the ideal thing for the next week. Great, okay, cool. If there's nothing else for now, I guess discussing on, then there's a separate thing of, I feel like we're doing this by the seat of our pants. So anything that is worth tweaking, we should try to do, and self-organize. If you want something, just build it yourself or get someone else to build it, or we could try to figure it out. And I don't really know what's going to happen over the next few weeks. Oh, can I talk more about stacks, please? Let me duck on that from, sorry, I don't know if you were watching on YouTube before coming on, but there is, a great resource on stacks. Let's see if I agree with that resource. Dan added it, yes. Okay, yes, Dan added it. And Barbara Fantecchi, who is actually on Zulip and is in AGITTOC, she also has something called Stacks for Everybody that I thought was really nice. I think, actually, maybe the last thing I'll say about stacks, and I'll let it, local, global, and discrete continuous. Yes, and That's a deep question. Okay, Rachel's question was if there's a connection between local/global and discrete/continuous. I need to, that question is making me think a lot. I want to say definitely there's something there or no. Okay, I can't, yeah, let me ponder that and maybe talk more in Zula. And the other, yeah, right, that's a good question. Okay, I have to stop thinking that or else I'll just, and the other thing is there's a great article, Mumford has a, I wonder whether people in the know will agree with me, has the best article on stacks does not have the word stack in it at all, which means that some people who know about this will guess what I'm about to say, which is Mumford's Picard groups of moduli problems, I think, something like that. Just, something like that. But of course, this is good only for, this is really intended for sort of people who are at the grad student level of detail too. It's not like a comfortable, it's not a short, I mean, and he also doesn't say what a stack is, it's just all about stacks. And a really bad thing to read is Deline and Mumford introduced the notion of a Deline-Mumford stack. And I think, well, don't read that. I think it's horrible. Like I think any reasonable person thinks it's, the paper is brilliant, but the paper is horrible. Great, thanks. Julian has the, Rachel has no word. Good, great. Okay, cool. So, okay, great. So that was experiment number 1, and we will see what happens next week and where we might be in the following weeks. Okay, thanks everyone. I'll see you virtually very soon, and then we'll talk more next week.
Thanks, Robbie.
It's on, Robbie.
Thanks very much for doing this.
Thank you.
Thank you.
You take care. Have a good weekend.
Thanks, you too.
Thank you.
Thanks.
Thanks, bye.
Thank you.
Thanks. Of course, some people are joining right now, unfortunately. But French flag. Great. And I guess shepherds or anyone else, we could talk more about what to do and what would be interesting to see what people talk about. And
So I posted some links to the MSRI things in the lobby for the.
Good. I realize it's not.
I think that'd be a great place to say collect a bunch of links to some of these things.
I can imagine that there might be a desire for like a stream on stacks, just to toss references in. If people want to, they can.
Yeah, there's some people asking about stacks and moduli spaces in my group voids too. I kind of reposted some links and.
And you know, one thing I can almost imagine reasonably happening is if enough people are curious that we should just have like someone could explain, can explain stack. Like this is not necessarily linear. It could just be. It could just happen. I do know. So Jared Alper did. I mean,
that's a good point. That this doesn't have to be linear, right? Because yeah, I mean, David's here too.
Yeah, I was gonna say I get David.
You can twist Steve.
I bullshit David.
Take advantage of him not actually being on right now.
I shouldn't do it. Work on something else.
If he's working on something with you, then you don't want to do that. Slow him down.
Yeah.
Okay, or maybe not. Okay, you're regretting that now. Yeah. Both my so it shouldn't. Maybe we should keep that in mind. Maybe wait like not too long, but if not, people want to hear about something and it should be kind of more explaining something at a certain level. I think presumably it's somewhat clear that the level of people wanting to know about stacks and about moduli spaces it's a consistent level. Like it's a single. It's something which can be aimed at. Like it's something worthwhile for them. Okay, great. Okay, good. So I will go and rest a little bit, and then post stuff and touch base with people to figure out what to do next. So I'll end the screen share and wish you all a good day.
Bye, Ravi.